This is joint work in progress with Greg Moore and Constantin Teleman. So let's start. So a quiche is an abstract structure that acts on a quantum field theory, symmetries if you like. Infelicitously named, only that it hasn't really caught on. French agriculture names like sheaf, stalk, gerb, they all caught on quite a bit decades ago. Somehow French gastronomy doesn't seem to be as catchy. Okay, so and throughout will be the dimension, the space-time dimension of the quantum field theory that's being acted upon, the one that has the symmetries. So here are the basic definitions. The first definition is analogous to the definition of an abstract algebra. So a quiche is an n+1 dimensional topological field theory sigma, so that throughout will be depicted by that yellow cloud. And then there's a boundary, which is a topological boundary theory, and it's on the right. That's called rho. So it's the pair sigma rho. And that abstract structure can act on a quantum field theory. So here the quantum field theory it's acting on is called F. That's an n-dimensional theory. And the data of the action is a left boundary theory called F tilde and an isomorphism of the dimensional reduction along the interval with the theory sigma in the interior of the interval and the two boundary theories. So the analogy you should think of is from linear algebra. Quantum theory is linear. It's really projective, but in this talk, we're not talking about anomalies. So it's linear, and you should think of sigma as being analogous to an algebra, and rho being analogous to a right module. Often we can choose it to be the regular module. And it acts on a vector space F, and the action is given by a left module, F tilde. Okay, so this is usually called the sandwich, or let's think of it as a sandwich presentation, because it's the same theory F, but presenting it this way makes the symmetry more manifest. So there are mathematical foundations for topological field theory, and one of the ideas here is that if we stick within sigma and rho, these are topological field theories. The rest may or may not be topological. And
So is it always like a bimodule?
no. Well, it's a bimodule to the trivial theory, if you like, but it's really a one-sided, like a right module. It's a boundary. It's not a domain wall.
And
F is, in that analogy, a vector space. F tilde is a left module. Yeah. So we can use the mathematical theory of topological field theory to be on firm ground with sigma and rho, even if we're not with the quantum field theory. And I want to emphasize that rho is an important part of the story. We need both sigma and rho. And in that sense, the name quiche is appropriate because a quiche has a filling, sigma, and it has a crust, rho. Okay, there's also a calculus of defects, which is an important part of the theory. So what we're going to do in this talk is generalize from finite groups to arbitrary compact Lie groups. And so let me remind about finite gauge theory. These are finite group symmetries. So G here is a finite group. And there are three different constructions that we'll give of this structure, this quiche. And you should remember these numbers because I'll use them throughout the talk. So the first one, I'll explain them. First one is a finite path integral. The second one is using the cobordism hypothesis, as is the third one. In this one, what we attach to a point is some kind of bundles, perhaps bundles of vector spaces, bundles of higher categories, even bundles of numbers, just a number at each point of the group. And it's an algebra under convolution. So what's attached to a point is an algebra. And we also give rho of a point, which is basically the regular module. And the third one is a kind of dual picture, where what we attach to a point is a category of representations of the finite group. And again, we specify rho. So again, one of the main goals is to think through this picture in the case when we go from a finite group to an arbitrary compact Lie group. Okay, so here's the finite path integral construction, meaning it's a finite sum. So we're summing over these fluctuating fields, and in the bulk, in M, we have a principal G bundle. That's just a Galois cover if G is a finite group. And we have a trivialization, a section of that bundle, over the boundary, the parts of the boundary that are colored with the rho boundary theory. And so if we have a Bordism, remember a field theory, topological in this case, is a homomorphism from a Bordism category to something linear. So here we have a Bordism. It has an incoming and outgoing boundary. It's a morphism in the category from this manifold to that manifold. It has these green boundaries where rho is, and those are behaving as if they're not really there as boundaries from the point of view of the Bordism category. And what we do is we get a correspondence diagram of groupoids by looking at these fluctuating fields, by looking at the bundles with trivializations on those green boundaries. And quantization is linearizing that correspondence of groupoids. That's how you quantize. So to do this all the way down and make an extended field theory, that's work in progress by Scheinbauer and Walda. So if we have a closed n manifold, so remember that's codimension 1, the theory is n plus 1 dimensional, then we want to get a vector space. And so we have this groupoid bun G of these G covers, and the linearization is just to take functions. Okay, so here's an example. If we have S2, if we're at n equals 2, then the vector space that's attached here would just be one-dimensional, just the scalars, that's functions on this groupoid, and it would be the same in this disk. We would only see that. Okay, so the other two constructions apply the cobordism hypothesis, so we have to specify what we attach to a point with enough dualizability to construct the theory by the cobordism hypothesis. So we need an n plus 1 category in which our theory is taking its values. We need an object, which is the basic theory, and then we need this one morphism from that object to the tensor unit. That's the boundary theory. That specifies the boundary theory. So we can compute what's attached to the point by, from this picture I just gave you. This is to do the computation for this Bordism. That's going to compute this morphism, and so we get this correspondence diagram of these groupoids, and that's what we want to linearize. So if n is equal to 1, so that's quantum mechanics, if you like, we're acting on quantum mechanics, then there are a few different standard choices we can take for where to do this quantization. If we take the Morita category of algebras, then when we just quantize what's on a point, which is point mod G, we get the group algebra of G. So when I said before this analogy with algebras and left and right modules, here we actually have an algebra. And again, you can go through the correspondence and you'll see what's attached to this Bordism F is the regular module for this, the right regular module for this algebra. On the other hand, we could quantize in categories, and we'll get the category of representations or the category of modules for that algebra. And then the map F is a tensor functor from rep G, or just a functor from rep G to vector spaces, and it's just taking the underlying vector space. Okay, if n is equal to 2, we have to up our game and go one category level higher. And so, so again, there are two choices. Well, sorry, there's just one choice here. So we're going to take the 3 category of algebras inside the 2 category of categories. And analogous to the group algebra with coefficients in the complex numbers is a kind of group ring here with coefficients in vector spaces. So it's vector bundles over G. Again, we use convolution, push forward under multiplication. On the other hand, we can do a Morita equivalent thing, which is to pass to the category of representations, and then this becomes a standard fiber functor. Okay, so that's kind of old. That's how we do finite gauge theory, and different ways that we can do the finite gauge theory in these low dimensions. So throughout the talk, I'm going to give examples in low dimensions, but much of what I say will work in higher dimensions as well. All right, so let me show you just why this sandwich presentation of a theory brings out the symmetry and how it's used, just to show you some very elementary examples. So here's some notation. So if n is equal to 1, then what we're acting on is quantum mechanics. And so a quantum mechanical system is given by a vector space H, Hilbert space, say, which is the state space. And there's a unitary representation of time translations. That's the time evolution. So that's the basic data of a quantum mechanical system. Now, I didn't say on the first slide what I meant by F. What is a quantum field theory? And of course, there are lots of ways to treat it. There's kind of semi-classical way in terms of fields and formulas. We'll see a little bit of that. There's also a relativistic way inside Minkowski space-time. But mostly I'll be thinking of the Wick-rotated version of quantum field theory and the axiom system of Siegel, representation of a Bordism category. So we won't see this unitary time evolution on the next slides. We'll see its Wick rotation, which exists as long as the energy is bounded below. And so I'll write it in those terms. And now we want to talk about quantum mechanical symmetry systems with a symmetry. And so we also have a unitary representation of a finite group. Now the calculations I'll show you on these next slides are fine for the finite group, but they will be the same if we have a compact Lie group once we get the theory in place. Okay, for n equals 2, we could have just a two-dimensional, as I said, Wick-rotated field theory. Okay, so that's what I just said, that the manipulations will apply for compact Lie groups. Okay, so here let's think about the quantum mechanical case. That's n equals 1. So this is the theory F. You can think about this vertical direction as Wick-rotated time. And so the evolution on an interval of length tau is e to the minus tau Hamiltonian. And so here, this is the data that gives you this, quantum mechanics. But now we want to present it as this two-dimensional sandwich, so the reduction of this two-dimensional theory along this interval. Here in the middle and on this, well, what's the right boundary, even though it looks left on the picture, is that's a topological field theory. And then this theory is going to be what? It's just going to be the same Hilbert space and time evolution, where we also remember the symmetry. So we're thinking about it with the symmetry. That's what goes here. So what's pictured is a point defect, which is usually called an observable in quantum mechanics. And what does it look like in the sandwich picture? Well, it's a defect which runs across like this in general. And that defect it's supported on this closed interval. So in the middle, the defect is given by a bimodule for the algebra A, for the group algebra. You can think of that as a representation of G cross G op, two copies of G. And what's given here on the right is a morphism from this module into the operators in your theory. That should be equivariant. And then on the left, we just get a vector inside M. So you compute all those by looking at the link of a point. That's how you compute the defects. In the topological case, you just look at the link. In the case when it's not topological, you have to take a limit, an inverse limit, as the size of that link shrinks. So it might be the case that M is just a copy of A itself. That's the identity, that's transparent. We could have T being nothing as well. And so we could have a defect that's just supported, for example, on the row boundary. And that would be given by an element of the algebra, an element of the group algebra. Okay, here's a picture for n equals 2. And now I've shown a codimension 1 defect and also a codimension 2, or a point defect. And here I want to think about topological defects that in the sandwich picture are supported on this row boundary. So those are the ones that are usually of interest. There are also defects that can wander into the interior or be supported in the interior. Those tend to be more central. So for example, in this case, you would get a central element inside the group algebra. So again, you compute the link. So for example, the link of this codimension 1 defect is again 2 points. Sorry, it's not 2 points. On the boundary, it's 2 points. It's the zero sphere. But taking into account the interior, it's the 1 disk. And so we have to compute, to know what the defects are supported there, we have to compute the value of the theory here. And say in finite gauge theory, that's just the category of vector bundles, the underlying category to the fusion category. And similarly for this point in this dimension, the link is this disk. So it's a disk with this green boundary. So that's the way you compute. Okay, so here's a little easy manipulation. Supposing we have these 2 point defects. One is labeled by an arbitrary element, not necessarily a unit in the algebra, not necessarily invertible, but the other one is labeled by an invertible element in the algebra, an invertible defect, so an element of the group, say. And what happens when I bring it past, which I see that I didn't in this. No, I bring G past. That should have been labeled by G, sorry. That's a G up there. So what happens is that it conjugates the element of the algebra. And you can see that because you can just multiply both of them in the topological field theory by this kind of pair of chaps. And when you multiply, both of those are supposed to multiply to G times A. So we can use that idea to look at, this is a typical kind of manipulation with groups when you have a quantum field theory. And again, it could work in higher dimensions. So here we're looking at a correlation function where we have a bunch of observables at various times in our quantum mechanics. And we also have a group element inserted at some time in the quantum mechanics. And now we have an initial state and a functional at the end that are both assumed to be invariant. So that's a typical kind of correlation function that you might want to compute. And again, if you look at it in the sandwich picture, then each of these observables is given over here. It's the image under theta over here of this kind of line defect with these boundary points. But the one for the group is just supported over here. And these invariant vectors, being invariant, tells you that those are just supported on this right boundary. So the manipulation you can make is very simple. Because this is topological, you can move this defect without changing anything until you run into another defect. But when we cross a defect, we know what happens. It conjugates. And we can move up to the top. And now if we view these vectors and covectors at the end as a kind of domain wall with the trivial theory, you see we can keep moving the symmetry up, and then it doesn't appear anymore in the correlation function. And so what you find is the usual equation that when you move it past, when you insert this row of G, you get the action on the operators that you crossed. So that's just meant to illustrate why it's useful to have this separation of the topology from the quantum field theory. This is quantum mechanics, so that's fine. It's on good mathematical grounds, but the same argument in higher dimensions would apply to any quantum field theory. Okay, here's another application, what's called a selection rule. So here we have a correlation function again, as before, but maybe I wrote it wrong on the previous slide, I see. And what's written in between the observables is the Wick-rotated evolution. And again, we're operating on this, these invariant vectors and covectors, omega and phi. So over here, we get this picture where these modules or representations of G cross G op are telling you, if you like, in what representation these observables transform. That's what it means to be on that line. And so at the end, we have the complex numbers because we have invariant vectors. That's the trivial representation. And there it's a one-sided representation now. And so we want to say that this correlation function vanishes unless this tensor product of these representations is non-zero. And that's easy to prove because you just factor this by cutting over here. That's, again, in the topological field theory. You're factoring through this vector space, and that is this vector space. So if that vector space is zero, you know the correlation function vanishes. So that's the usual selection rule in quantum field theory. But again, we don't need anything about the quantum field theory. The argument is completely in the symmetry. OK. So we don't just need finite groups. This kind of finite theory in this path integral construction works for more general higher groups and so on. These are pi finite spaces. So let me just remind you quickly of that construction. So we take a topological space X, which is pi finite. That means it has finitely many path components, and each path component has finitely many non-zero homotopy groups, each of which is a finite group. So everything is as finite as you like. And we want to quantize by looking at mapping spaces into X. So for example, if we're on a closed top-dimensional manifold, then what we do is we count, in a sense, how many maps there are into X. So X to the W is the mapping space of continuous maps from W into X. Here W is a smooth n plus 1 dimensional manifold. And we count the maps, but up to homotopy. So we count how many different components there are, path components of maps there are. But we have to count with weights to account for the higher homotopy groups. And this is where the pi finiteness comes in. We need that sum to be a finite sum, and we need each of these numbers in the product to be finite, and we need the product to also be finite. So pi finiteness is coming in to make that sensible. What about on a closed N manifold? That's codimension 1 in this theory, so we might want to assign a vector space to that. Well, we take functions on the mapping space of again, continuous maps from the manifold into this topological space X. So these are the locally constant functions, factors through to functions on pi naught of the mapping space. So notice that pi finiteness is not used in writing down these functions. And in fact, if you keep going and quantize as an extended field theory in lower dimensions, pi finiteness is only used at this top dimension. So if we're willing to give up the top dimension, then we don't need pi finiteness. Now, pi finiteness would also be used if I want to write down an inner product on this function space. Then we would also use pi finiteness to construct the inner product. But if we don't ask for unitarity, then we don't need it. So the kinds of theories that we'll discuss are going to be truncated below the top, and they won't be unitary. Of course, unitarity is, physicists like to say in quantum field theory, there are two pillars, locality and unitarity. And if you think about representation theory, say of non-compact groups like SL2R, one studies representations before talking about unitarity, and then studies separately unitarizability and so on. And here we have a Bordism category. We're representing linearly, and it's the same philosophy. Okay, so to do the Lie group, we are going to relax this condition of pi finiteness in the first of the constructions.
Can I ask a question about that?
Yep.
So you need finiteness to define the inner product.
Mm-hmm.
But as, for instance, you and Mike emphasize, part of collection positivity is first reflection. And you don't need pi finiteness for that. Is that right?
Yeah, I think that's correct. Okay, so we want to generalize much of this to compact Lie groups. So let me emphasize that it's a much bigger step to go to non-compact Lie groups. For example, we'll use the representation category of a compact Lie group, and representations of a compact Lie group are, well, compact Lie groups are rigid, they don't deform, and the representations also are rigid, they don't deform. So the category is still semi-simple, but for positive dimensional Lie groups, there are infinitely many simple objects. If you go to a non-compact Lie group, for example, the integers under addition, then first of all, representations, even one-dimensional representations, deform. And secondly, you have things like Jordan blocks, which are reducible but not indecomposable. So you see this non-semi-simplicity right away. So we're sticking to compact Lie groups here. And the two new features to emphasize, the first one is what I said on the previous slide, that we're going to abandon trying to get invariant numbers for n+1 manifolds. That won't be possible. So this is an n-dimensional field theory. It's a map out of an Bordism category of n manifolds. But what you attach at the top is a vector space rather than a number. So it's once categorified in the sense that the values are once shifted, we could call it once shifted, from what you might expect. And the second point is that derived geometry is going to play a role in the constructions. We'll see derived things come up. Okay, so sigma, the filling, if you like, of the quiche, has a semi-classical description, and that's what we heard about in Yaki's talk, in terms of a limit of pure Yang-Mills theory, or BF theory, which has been, so this idea that that should be what's in the quiche that corresponds to a compact Lie group has been much around. And here's, again, this was in Yaki's talk, why this topological limit of Yang-Mills is BF theory. So we look at this, this Lagrangian, as Yaki had, where here A is a connection on a principal G bundle, and B is an n-1 form with values in the coadjoint bundle of that principal bundle. And so you can write down this expression. Notice it has the Hodge star operator, so it's using the Riemannian metric. But we can integrate out B, as he did, and see that this is the standard Yang-Mills theory with this coupling constant. On the other hand, if we take e to 0, then this term just disappears, and what's left is the Lagrangian of what's called BF theory. And notice the metric dependence also disappears, and so heuristically at least we have a topological field theory. And so you can interpret part of what I'm going to say is defining BF theory using the technology of topological field theory as an extended field theory, but without this top n+1 dimensional layer. Okay, and I learned this week that some related ideas to what we're going to say appears in these recent papers, but in different forms. Okay, so as a kind of motivation, let's look at what compact Lie group symmetries in quantum mechanics would be. So we have the same data as before, but now G is an arbitrary compact Lie group, need not be a finite group. And what we might put in the middle would be two-dimensional Yang-Mills theory. That's what the motivation on the previous slide was. And so let's just see what the partition function is if we think that this is going to make sense on a closed surface, sigma. So two-dimensional Yang-Mills theory depends on an area form, in fact. We don't need a whole metric. And this is the formula, up to constants, for the partition function of this Yang-Mills theory involving, as you see, the area. Well, we can take that limit as e goes to 0. That was the limit we're supposed to take to get a topological thing. And indeed, we get something that doesn't depend anymore on the area. So it is a topological quantity. It's a familiar quantity from two-dimensional field theories of finite type. But this is a sum over all the irreducible isomorphism classes of irreducible representations, which is typically now an infinite sum. And this sum certainly diverges if the genus is at least 1. For example, for the genus 1, it's counting how many isomorphism classes of irreducible representations there are. So that's infinite. So that's why we're going to abandon the top. And if we think in higher dimensions, if we have an n-manifold X and we cross with the circle, and if we were to make sense of that in the topological field theory, the value of that partition function is the dimension of the vector space. And typically, these vector spaces are infinite dimensional.
Why is there notches for G?
May have missed something.
Why does this sum diverge? Oh, sorry, that's wrong. Sorry, I have that completely backwards. It diverges when G is 0 and G is 1, yes. Not for bigger G. For bigger G, it converges. I'm sorry. Yes, thank you. That's correct.
Written that a function.
Yeah. But But the point is it's not finite on all two manifolds. Yes, correct. Okay, so sigma at best can be a once categorified n-dimensional field theory. And now what are the values on a circle and a point? Well, we're going to get some, on a point, we're going to get an algebra of functions. For a finite group, we have the group algebra. Here we want some algebra of functions under convolution. And what we're going to get on the circle are the central functions in that algebra. But what kind of function space should we take? Well, if we think about these point defects, we want to have a point defect that's labeled by a group element. But if we compute what the set of defects supported on that point is, it's going to be the vector space of functions that we chose. So it seems we should take some kind of space of distributions if we're going to get those standard defects labeled by a group element G. And in fact, when you do representation theory, even for a compact Lie group, once you have infinite dimensional representations, then the same representation occurs, so to speak, in many guises. So here we could think about the regular representation of a group G. That is the one we're interested in. It's the functions on G. And it depends what kind of functions we take. We can take algebraic functions, smooth functions, continuous functions, L2 functions, Sobolev functions in between, distributions, and lots and lots. So these are topological vector spaces. Having an infinite dimensional vector space without a topology, it's good for some purposes, but not certainly for this one. And these are all dense inclusions. And we want to consider those representations to be the same. So we encounter that issue also in field theory, in the higher up. Okay, so how do we construct this from the cobordism hypothesis then? So here we need some finiteness to be able to apply the cobordism hypothesis, and so we need dualizability. And if we're in this low dimension, n equals 1, then it's very simple, because we can take our target 2 category to be algebras in, well, in this case, of 1 category. But in general, if I take algebras, then any object is 1 dualizable. So that's a basic fact about this higher algebra. And so any algebra anywhere determines a one-dimensional theory. And in particular, if we have C prime as a symmetric monoidal 1 category, like appropriate category of vector spaces, then we get a one-dimensional theory. So this right away is an example of what we'd like to be a 2-dimensional theory, but at least it's a once categorified, once shifted 1-dimensional theory. So here we take algebras in vector spaces, where we take a good enough category of vector spaces to have the kinds of topological vector spaces we want. And then we can take this convolution algebra of distributions and the right regular module, and that's one way we can construct this theory for quantum mechanics. On the other hand, we could do the dual construction, where we take the category of representations. Again, that's a nice semi-simple category, and rho is now the functor that gives us the underlying vector space, which again might be infinite dimensional, so we need a good category of infinite dimensional vector spaces. Okay, so the kind of higher algebra we need, here it's not so high, but that kind of higher algebra has been developed quite a bit in algebraic contexts, right? Algebraic geometric contexts. And here we need it for topological vector spaces and need a symmetric monoidal category of topological vector spaces. So nice categories of topological vector spaces aren't so easy to come by, and there's a lot of recent work, people like Clausen, Schulze, and so on, that are constructing good categories of topological vector spaces. And on top of that, we need the higher algebra going on up as we go up in dimension that will allow us to make these constructions. So that's all work in progress by the Munich branch of this collaboration. So you'll see them a few times, who are developing this higher algebra and proving the kinds of finiteness theorems that one needs to implement the ideas that I'm discussing here. Okay. So now let's go back to this kind of motivational picture with these fluctuating fields, the BF theory that we heard about in Inyaki's talk, and we'll hear much more about later this afternoon, Alberto. So let me give the semi-classical description of, we're interested in sigma rho in this quiche, but I'll just say also how it couples to this quantum field theory in general. And so what we have are these three fields. So the two of them, the A and the B that we saw before, this is a connection on a principal G bundle, and this is n-1 form with values in the coadjoint bundle. Those exist in this bulk in the middle. And on this row boundary, we have one other field, which is a flat section of this bundle with connection. So in particular, it enforces the condition that the connection be trivializable on that boundary. That's the same kind of thing. If you specialize to a finite group, you'll recover what we had for a finite group. And on this boundary, there's a boundary condition. So if you like, this has two fields, but it's first order. So to give kind of elliptic boundary conditions, we need to give a condition on half the fields. So here it's the condition roughly A equals 0, so that's a condition on A. And over here it's a condition on B, which is the condition that B is equal to the current, which is the same kind of field. And it couples there in the usual way. We have a quantum field theory, F, which isn't pictured here, which has a G symmetry, which means we can couple to a background gauge field, is the way quantum field theorists say that, and that's how this couples to A on this boundary. Okay, so the equations of motion of the BF theory, I think they were given in the previous talk, tell that A is a flat connection, that the curvature is 0, and in fact tell that B is covariant constant. But we're seeing the flat connections embedded in the space of all connections. And so that's some kind of motivation that when we restrict now to flat connections, we remember, at least infinitesimally, the embedding into all connections. And that's where we're going to treat it as a derived stack of flat connections. Okay. So again, we're not going to use all connections. We're just going to use flat connections. And one thing about that is we can't take quotients or gauge, because gauging would involve integrating over all connections, and we only have the flat connections. So here's, if we're standing at a flat connection inside some moduli space of flat connections, this is the deformation complex. So the tangent to A, a deformation of A, is a one form with values in the adjoint bundle, and that's kind of the geometric deformations. But we have the gauge transformations, which infinitesimally is given by sections of the adjoint bundle. This is the covariant derivative mapping here. So that's the Stacky direction. These are the automorphisms. On the other hand, we have the derivative of the zero curvature equation that cuts out the flat connections. That's, again, the covariant derivative now mapping to closed two forms. And so this makes a complex if we're standing at a flat connection, and that's the deformation complex for this moduli stack of flat connections. Well, there's a little maneuver you can make here, which is that this deformation complex is quasi-isomorphic to this one. So what does it mean? Well, we're working, you should think, in just a small ball where we have the Poincaré lemma, not over globally sections, but we're working in, so to speak, arbitrary manifolds, arbitrary smooth manifolds, and this is the kind of thing that you check on small balls. And so what you see here is the de Rham complex. And so if we're going to study this derived stack of flat connections, then we'll see the de Rham complex. Yeah.
So in the finite group case, if I replace rho by some other boundary condition, then that can be understood as gauging the
Correct.
symmetry G. Is there something like that we can do here?
I don't know of anything like that, just because the heuristic is you want to integrate over all connections, and we won't have all connections.
Yeah, no,
just
I
have
certainly
flat.
agree with that intuition.
Okay,
But,
yeah, so I don't know a substitute.
But does that mean that rho is unique here? Like, can we keep the same sigma but choose a different rho?
You can certainly choose other rows.
Right.
For example, you might quotient or gauge by a finite subgroup of G, even if G is a positive dimensional Lie group. So that you could do, right? So there are things you could do. I'm just saying to quotient by the whole Lie group is in what we're saying. I don't know how to do that.
So in this context, changing rho while keeping sigma should not be viewed as gauging.
Well, you can partially gauge. But in other contexts, you can also change rho and not, I mean, you might change it and do other things too. Okay, thanks. So I think what we'll hear about from Alberto is
certainly gauge and take invariance for back connection. The problem is that numbers may or may not be finite if you try to go numerical methods.
right.
We're not solving that problem.
So we'll hear later, I think, we'll hear about BF theory, probably in the BV presentation, and there we'll see the fields, the fluctuating fields that correspond to these, to the de Rham complex. So, long history of work on that. Okay, so, yeah, David.
Same thing. So
Okay.
you can still specify like a non-trivial topology on the G bundle. Is that right? Like the section S is a flat section, not necessarily the trivial bundle, but you can. Is that correct?
Well, if you have a flat section of a bundle with connection, it is a trivializable bundle in particular without the connection
Yeah. Okay.
on that boundary. But if you had a complicated topology,
Yeah.
you might be doing an extended field theory. So this could be in lower dimensions where we're not worried about this cutoff at the top. And you could have the bundle being trivializable on these green boundaries, but not trivializable on the whole thing.
Okay.
But if we are taking the product with an interval, then of course, and we're only doing flat connections, then the flat section at one end is going to propagate
Right.
throughout. Okay, so now we repeat the construction we saw with finite groups, and we take the groupoid now of flat G connections, and again, trivializations on these green boundaries, and we do the quantization. So again, to get an extended field theory, we need to know that this finite path integral construction, which is no longer finite, but this kind of quantization of these correspondences can extend to non-pi finite spaces. But I think that part should be fairly straightforward. Okay. So again, when we do the quantization, we're supposed to take functions on, for example, for a closed-end manifold, we're instructed to take a vector space of functions on bun G, but now we have to decide what kind of functions. So if we're in the case n equals 1, and we're quantizing on this interval with both boundaries colored by the row boundary that functions as a closed manifold in the Bordism category, so we get a vector space, and we're exactly trying to quantize G. The space of these bundles, the stack, is just the Lie group G. So we exactly run into this question. So when we're doing this kind of quantization, we have to decide how we're going to do that, what topological vector spaces. Yes?
So you say on the previous slide, yeah. So you go to correspondence of groupoids, but shouldn't you treat this as a derived stack of like bun G flat? Or?
Yes.
Okay. Yeah.
Yes. Okay. I mean, treat it as a derived stack. Okay. Absolutely.
Sure.
Okay. So this slide is just a little bit of a aside, so I'll just say it quickly, which is for n equals 2, you can view the BF theory as a Chern-Simons theory, but in this case as a Chern-Simons theory for a non-compact Lie group, namely for the cotangent bundle of G. So that's a Lie group. And you need a level for this Chern-Simons theory, which amounts to just the standard symmetric pairing on the Lie algebra plus its dual. And you see that a connection for this Lie group is equivalent to a pair, which is roughly the A and the B field that we talked about before. And if you write out the Chern-Simons form, then that's a form on P, on the total space. But up to an exact term, it descends to the base to be up to 2, the usual BF kind of action. So in n equals 2, you can think about it in terms of this Chern-Simons theory, which is sometimes useful. Again, we get flat connections now for the pair AB, and you get the usual equations of motion. Okay, so how should we construct this? So I said at the beginning there were 3 constructions for a finite group. The first is this finite path integral, and that I've discussed now. We replace the bundles of G covers for G finite with this derived stack of flat G connections, and we do that kind of quantization. And the other two were with the cobordism hypothesis. So these are the constructions that will give this BF theory as a once categorified theory once the higher algebra is in place. So we have different motivating cases that we already know. For n equals 1, we had two different quantizations. In the case when G is an arbitrary compact Lie group, we had this convolution algebra of distributions, I guess one quantization. And for n equals 2, we had two of them. We have this convolution, this convolution algebra of sheaves is the one that's relevant here. So the proposal, at least for n equals 2, this was for a finite group, and now we're going to do this for a Lie group. And so again, we want to take a convolution algebra of sheaves, but now the sheaves have fibers that are topological vector spaces. And again, we can have the right regular module. So, as I said before, we need the underlying algebra to make sense of this proposal, and that's what's being developed. Okay, so in higher dimensions, you might think that then we take, again, a convolution algebra of sheaves on the Lie group, but now the fibers should be higher categorical in some form. But there, I think the higher algebra is a little bit further off to make sense of that. Okay, the dual construction, we start with the category of representations and a corresponding map to the tensor unit. And in all the motivating constructions, it's the category of representations of G. So I've already said for a compact Lie group, that is a nice category, albeit not finite. And in fact, it's not only a nice as a category, but it's a symmetric monoidal category. And that means it's as commutative as you like, and the level of commutativity that's appropriate if we're doing the thing in n dimensions is that it's an En minus 1 algebra. And so that then, once this higher algebra is in place, will be n-dualizable inside En minus 1 algebras, inside the appropriate category. And so this leads to a dual construction. That was the third one that I gave, where, again, what's attached to a point is now this representation category of G as an En minus 1 algebra. Yeah?
Case, if you take, I guess you would call the left boundary, F tilde,
Yep.
to be also rho. So you have rho on the two sides. That corresponds to a spontaneous symmetry breaking phase of the symmetry G. Now, in your case, G is continuous. What if I take both sides to be rho? Naively, I would say that's a spontaneous symmetry breaking phase. But I don't think there's a ghost on boson, right? Because everything is topological.
I think I need to think about that after, if it's okay. Quick comment, because that's a little off.
You put in a gapless boundary condition. So in Inyaki's talk, right, you could put in a topological one, as in Dan's case, and you get something that's a gap. Also, it's gap, but it's slightly weird. It has infinitely many vacua. If you take a gapless boundary, so you put modes that are the Goldstone boson modes on that boundary, then you get the correct symmetry breaking for continuous symmetries.
Okay. So let me, the last thing I want to do is show you a little bit of a phenomenon that comes up when we start calculating defects in this theory. And so for simplicity, I'm going to restrict to n equals 2 for the remainder of the lecture. So here's the codimension 1 defect. So the usual story in the physics that started this off is when you have a Lie group symmetry that you have these topological defects in codimension 1 labeled by group elements. So let's see where that is. So in the sandwich presentation, these defects will be supported on the rho boundary, and it's codimension 1. And what's the link of a point? Well, we've already seen that. The link of a point is this one disk with boundary on the on rho. So this rho boundary. So that's what's depicted here. That's the link. And so we have to give, as we move along our codimension 1 support of our defect, we have to give an element, we have to evaluate the theory on that link, and then we have to give an object in HOM from 1 to that evaluation. So we always give an object from 1 to whatever that evaluates to. So here it evaluates to the category of sheaves, the whatever kinds of sheaves we're doing on the group, and then we have to give an object in that category. So we're giving a sheaf on the group, and of course, if we have the right category of sheaves, then there is a simple skyscraper sheaf at each group element, and those are the defects that are talked about in the physics literature. But again, quantum theory is linear. We can have superpositions, and you can think of an arbitrary sheaf of this type on the Lie group as being a kind of superposition of these defects. Typically, of course, not invertible. Okay, so now let's go to point defects. So if I have a point defect, also called sometimes local operator, then we expect a vector space of those operators. And so let's compute what that is, this vector space V. I'll compute it in 2 different ways. First, by quantizing the derived stack of flat connections to compute the value of the theory, and then using the cobordism hypothesis. So here we have our point, which is the support of the defect. It's again on the row boundary. It's this topological defect. And so the link is this, this disk with this row boundary. And for a finite group, we computed that the vector space is one-dimensional. That says the only point operator is the identity, so it's as if it wasn't there. We don't get any interesting point operators. But now we have to take the derived stack, it should say, of flat G connections. And, well, what is it? So there's only one connection, flat connection on this disk. It's already trivialized on the boundary, and so it has no automorphisms. But we're doing it in a derived way, and so the tangent complex is this de Rham complex, this relative de Rham complex. And to compute it, we just need to take the cohomology. The relative cohomology is only in degree 2, and it's a copy of the Lie algebra. And so if you remember the degree 1 part, that's the geometric part. So the degree 2 part is one derived direction off, so it has number 1 in the derived direction. And so now we have to take functions on that, and so we'll get the dual to the Lie algebra. We're taking complex functions, and that now is in degree -1 to take the dual. So what we get is the symmetric algebra on this, but this is in odd degree, so the symmetric algebra with the cojoule signs is secretly an exterior algebra. So we get this, we get Sim0, which is what we saw before for a finite group, but now we get these derived pieces as well. Okay, what if we do it starting from the cobordism hypothesis, where what we attach to a point is some convolution algebra of sheaves on the group? Well, then we have to calculate this disk. We do it by cutting at an equator, and so we have to start by computing the vector space here, the category here, but that's the category of sheaves, we know that. And now if we do the half disk, well, that's going to be the tensor unit in this tensor category. That's just the skyscraper sheaf at the identity. And now when we put back the other, which really should be a raviolo, where I take 2 of them sort of on the same side, kind of cut raviolo or something. Anyway, that's going to be endomorphisms of this object in that category. But now computed in a derived sense, and if you compute it in a derived sense, you get a similar answer to what we had before, but you find it's in degree +1, not -1, and it's the Lie algebra instead of the dual Lie algebra. So that's a little bit confusing, but nonetheless, you get the same kind of answer. And so these 2 answers seem discrepant, but if we remember a little bit about quantization, then we can see why we might get 2 different answers. And namely, we could use as motivation this BF theory, which in this dimension is also T star G Chern-Simons, and we could quantize by solving the classical equations, essentially on this disk with that boundary cross time, in the rent signature. But in any case, it's topological theory. We get these flat connections, covariant constant B, and then on the boundary, this flat section. Well, so what are the solutions? As we said before, as a connection, there's only the trivial connection with no automorphisms. But if you think about the field B and its gauge transformations, then you're allowed to shift B, which now has to be constant. You can shift it by an element in the dual of the Lie algebra. So the moduli stack is point mod G star. But now you have to remember the derived part of the space of connections. And so in the end, what you get is this symplectic vector space, which has both the G and the G star in degrees 1 and -1. And when you quantize, you polarize that standard symplectic vector space, and that's how you get the two different answers from that point of view. Okay. So we have these defects, these point defects, which are sitting in derived geometry, and you can ask, can they be realized in a theory? It's possible when you have the theory that they always map to 0 or something like that. So I'll just end with a little example to show you that they might not be 0. They're not 0 in general. But we need some kind of derived piece of our field theory to really see it. And so here we're using topological twist of the two-dimensional theory, this kind of supersymmetric theory, which has this derived piece, namely the B model. So, so this B model is going to sit here. So it's a topological field theory. We can have symmetries of topological field theories. It didn't have to be a non-topological quantum field theory. And so the theory is given by a Calabi-Yau manifold M, which has a holomorphic group action. And how do we define that field theory? Well, we can define it using the cobordism hypothesis, where what's attached to a point is the derived category of coherent sheaves on the manifold M. And we could compute then what's attached to the circle is some kind of Hochschild cohomology, which is this cohomology with this bigrading, but total grading is what we'll use. And now, when we want to incorporate the G action, which is what happens with F tilde, then, well, we're going to get these topological point defects. So if you remember, we had this exterior algebra, I'm using this one, on the Lie algebra. And so we could take the degree 1 element, which is just an element of the Lie algebra. That element of the Lie algebra gives a holomorphic vector field on M. And so it gives us exactly a degree 1 element inside this vector space, F of S1. So that's where we could see those defects. And now if we want a correlation function which is non-zero, we can do the following. We can take M to be an elliptic curve, and the group, the elliptic curve is a group. It acts on itself by translation, so that's going to be our Lie group. And now we'll evaluate a correlation function on the two-sphere, where we have this topological defect here. That was in the sandwich presentation, this rho defect, given by an element of the Lie algebra of E. And then we have something we need also of degree 1 to get a non-zero answer. And we're going to take something in the first cohomology with coefficients in O, which we'll interpret as a kind of principal part for a meromorphic function. And so now we can make the correlation function of these two. It's not hard to compute, and what you get is the sum of the residues of, take that quadratic differential and take the interior product with the vector field. Anyway, that's just to illustrate, by here a topological example, that these derived defects can be non-trivial. So that's all I have to say. As I say, we're kind of at the beginning. This was just conceptually to show some of the issues that arise when we generalize from finite groups to compact Lie groups. Of course, once we straighten those out, higher groups that involve Lie groups and abelian Lie groups higher up, all that should also generalize quite nicely. Thanks.